Okay, welcome to the last lecture of 105, probably your last lecture of this semester. So I want to mention final exam. I just sent you an announcement, final exam, which will be same as the officially scheduled final exam. Unfortunately, that's Friday, the last day. December 15, Friday, we have had the honor of having the last final exam for many years now. So these are also late, 7 to 10 p.m. You'll be here, exactly the same classroom, all right? And I'm planning to have roughly 7 questions. And each question may have something like 3 or 4 sub-questions. So the degree of difficulty is kind of between midterm 1 and 2. So 2 is maybe on the short side, 1 is on the long side. I'm aiming to hit in the middle, okay? In terms of coverage, it's pretty much all the materials. Now that sounds kind of very general, it's a lot, but you can almost think of, well, what are the topics we have covered so far? So going backwards, we have talked about differential amplifier, okay? So certainly there will be a differential amplifier question. We talked about multi-stage. And so, reasonable to expect that. We have talked about kind of the frequency response. This will be, think of something like your lab, that you have transistors, you have capacitances. Now there are capacitance from the transistor for the high pass side. Low pass side, usually it comes from the external capacitors, right? And there will be, kind of current source, current mirrors. That's a topic. And don't forget, we have talked about op-amps. From the very beginning, op-amp circuits, and including non-ideal op-amp. We have talked about devices. So MOSFET, for example, that we have talked about. 1, 2, 3, 4, 5, 6 problems. There may be one more, or they are not exactly mapping to the questions. Yes?
How much is it going to be for you on midterm 1, midterm 2? I mean, obviously the fundamentals that we learned in midterm 1, midterm 2
right.
used for these?
Will be used for this.
Like specific midterm 1, like specific PN junction, like...
So, all PN junctions kind of will be showing up here. And so you're more likely to see like integrated questions. So you'll be more than a PN junction, but the PN junction is inside a transistor, for example. There'll be less questions on like details of diffusion equations, diffusion current, and so on. There'll probably be more questions on, for example, capacitances that relates to capacitance in the MOSFET, what affect the transistor performance, and so on. Okay. So another thing that we would like to kind of remind you to look at is the DC performance. So large signal, basically, large signal. in principle, when you solve a circuit, either differential circuit, multi-stage circuit, you solve DC first and then you solve AC. We might give you separate questions rather than just lump everything into a big question. Okay. This will be, as before, closed book. And 4 pages, notes allowed. And you can reuse the notes before. You can make new notes. Whatever you want to do is fine. And I also mentioned bring your calculator. Midterm 2, you almost can do without a calculator. Midterm 1, you kind of just punching a lot of calculator, punching numbers. This one will be a little bit more than midterm 2, less than midterm 1. Okay, any other question related to midterm? Okay, we have also agreed to give Ita Kappa Nu 10 minutes to talk about the survey. It's all online now, but they are still obligated to come. So we'll finish before 4:50. So let's review what we have talked about. Differential amplifiers. Differential amplifiers are supposed to reject common mode. So if you can somehow sense your noise separately, on top of that you have your signals, then your signal to noise ratio will improve because your signal will be amplified by the differential mode. So the key is the signal, okay, signal is amplified by the differential mode gain. So AVD, that's differential mode. So this is a high gain for differential mode, just like op-amp. And your noise riding in the background, that's applying to both channels, and you're going to see a common mode gain. Okay, and common mode gain is usually much less than 1. Okay, so when you do signal to noise ratio, as in all signal processing, it's all about signal to noise ratio. When we do signal to noise ratio, you'll see after the amplifier, now you have this factor appearing here. So this is the raw signal to noise ratio in the say raw magnitude. It may be very poor. Signal is here, noise is here. It's almost the same. But after it goes through the differential amplifier, now you have the ratio of the differential mode gain to common mode gain. So that's exactly the common mode rejection ratio. So you improve your signal to noise ratio by the common mode rejection ratio. So that's why this is an important number. When we look at op-amp at the beginning of the semester, we emphasize this common mode rejection ratio for this precisely this reason. And while the signal is in the differential form, so in the very first stage, you need to kind of design your probe carefully, your input carefully to create that differential input. Once you create that differential input, you can amplify that differential signal by another differential stage. And if there are additional noise added in between the stage, well, they are likewise going to be rejected by the second stage's common mode rejection ratio. So you do that multiple times until you have sufficient gain. Eventually, you need to convert that to a single-ended output. We'll talk about that today. Before that, the previous differential amplifier, so the standard differential amplifier we talked about, have resistor load. Okay, so it's something like this. And we said, well, the differential gain is kind of equal to the half circuit. And the half circuit, the gain, so AVD, is basically equal to minus GM RD, right? and RD is the resistive load. So just like common source amplifier, single transistor common source amplifier, RD is not very large. RD is on the order of, say, kilo ohm. So GM times 1 kilo ohm, it's moderate gain. Very often we like higher gain. So just like in single stage amplifier, we replace the load by active load. And we do exactly the same thing here. So we'll have a differential stage where the RD is now an active load. This active load in real circuit will come from a current mirror. So for example, this will be coming from a reference circuit. So this will be a reference circuit. So here will be a reference, and okay, here will be VDD. So that provides the bias to the load. So now the impact is, so again, we can, it's still anti-symmetric. This is still virtual ground. We can still convert it to half circuit. So this is the same half circuit as we have looked at before. So this half circuit looks like a common source with an active load. And active load has higher impedance. So you look up here, you see the output impedance of the transistor. So you see R0, 3, and you look down here, you see the output resistance of transistor 1. So the combined resistance will be R01 in parallel with R03. So your gain now become GM1. So the amplifying transistor here is GM1. So it's GM now times this output resistance. Output resistance, as we mentioned, are generally much bigger. RO is usually on the order of 100 kilo ohm. So you see you make up 100 times of the amplification you can get from transistors. And there are other benefits, as we mentioned. They are smaller, they are really more efficient, density can be higher, so output swing can be better. The output swing will be limited by the voltage drop across the resistor, whereas in the active load, you can push it all the way until you are on the edge of saturation for this active load Q3. Okay. You can play the same trick just as we do in cascade amplifier. So this is a cascade version of differential amplifier. Your key main amplifier is here, Q1 and Q2. Cascade means you feed it to a common gate stage. So you feed it to a common gate stage, and you have a cascade current source load. Okay, so this cascade, again, you think of it. This is going to the current mirrors. Okay, so this is going to current mirrors here that generates the bias. Okay. And you'll have this current source that generate the required bias for the load. And if you recall, you get magnified output impedance. So again, the half circuit, okay, so the half circuit, just like before. Now you look down here, you'll see amplified output resistance. The output resistance for here, this will be GM3 times RO3 times RO1. And if you look up, this is amplified resistance. This comes from the summary of that single transistor with connected resistors that we talked about. You should keep that notes handy. Okay. So this will be RO5 and RO7. Okay, so GM is remaining the same, but now you have much larger output resistance. So you will have GM times this RO N side, RO P side. So this is RO N side. Looking up is RO P side. So they are in parallel, and GMRO is a big number, something on the order of 100. Okay, so the typical number here is about 100. So it's 100 times of the previous single transistor load and amplifier. So you get a gain that is now square of GM times R0. And so if you get a gain of 100, now you can get a gain of 10,000. So that's a pretty substantial increase. Okay, yeah, question?
Since we already have a current source at the bottom,
Yeah.
what's the relationship between the two current sources?
This current source and the current source that bias this? Bias the active transistor? Yeah, so often you will see actually they come from the same source. You could do mirroring once and then connect the bottom two, or you can do something that actually the whole chain is connected to NMOS here. It's possible to have alternative design that you for example, a simple design, you could add a resistor here which set the current, and then you can have NMOS here and another NMOS here, and that could be your bias generator, and your current will be set by this resistor. Or other type of circuits. Okay. So this is like a building block, Cascode. We learned Cascode before. Now we ported the Cascode into the differential geometry. Okay.
In practice, is it a standard way if we want a large resistance, we replace it by a Cascode amplifier?
Yes. Cascode, if you do a two-port model of this amplifier, so if you do a two-port model, so think about multi-stage amplifier, we always think about the two-port model. If you do a two-port model of the whole thing, the input you're looking at the gate, so you still have kind of infinite impedance. So your V in, which is VID over 2 is applied here. The output is going to have, let's look at the current output stage, right? So this will be the standard output model. And the current flowing through here, so if this is a current source, this whole two-port model have the same current because all transistors are chained together. So this current source is basically still GM1 times VGS1. So here is VGS1. Okay. But the output resistance is what we look at here. This output resistance is RON in parallel with ROP. Now the gain is the same current going through the much bigger output resistance. So output resistance here boosts up your gain. So we obtain higher gain this way without actually the adverse effect of the Miller capacitance loaded bandwidth reduction, if you remember the bandwidth part. So Cascode is kind of a very nice building block. Okay, so the last important building block that I'd like to talk about is, we could have one differential stage. We could follow a differential stage with another differential stage. So these are multi-stage differential amplifier. Ultimately, usually at the final output, it's a single-ended output. So we will convert from differential signal chain into a single-ended one. So how do we do that? Turns out there's an extremely simple circuit for doing that. So this is the circuit that will do the function. You say, well, this looks similar to what we have seen 2 slides ago. So let me scroll back 2 slides. Okay, 2 slides ago. This is the differential amplifier with active load, with a current source load. Okay. So take a look at that. Now I'm going to scroll back to the converter that produced single-ended output. You spot any difference? See any difference between the earlier circuit and this circuit? Q3 is forced into, they are always in saturation. In order for them to work properly, they are forced to operate in saturation. But indeed, we have this extra wire connected here. Okay, so this is not only a current source mode, it's a current mirror load. So it's a current mirror load. Well, we are now combining current mirrors as a load to a differential amplifier. Let's think about whether there are problems or not. So differential amplifier, we bias the whole thing with a current source down here. So we bias it with I. So that's our DC bias. And we say half I over 2 flow. These are large signal DC value. Flow through the left chain. And equal amount of current, I over 2, flows through the right side. On top is the current mirror. So both sides, again, we choose transistors that are well matched. So no problem. The currents are equal between Q3 and Q4. So everything is equal. So they do not disturb the DC operation of the differential pair. Now let's look at, so that's what's kind of detailedly described here. Just to look at the DC mode. So it's half I, everywhere is half I. And if we take the output, so where do we take the output? We take the output now from only one of them. It's no longer the differential mode. So this is the output. Okay, single-ended output. Okay. So now it's all balanced, half I everywhere. So at DC mode, there's a 0 current. So current is 0, okay? So I is 0 in the DC mode, okay? So now let's look at when we apply differential input, okay? So this is the differential input here. Differential input, we have positive voltage on one side, negative voltage on the other side. So the right side will have more current. The additional current is this small I here. Okay, so small I flowing down. Now on the right hand side, it's the same small signal current, but it's flowing up. Okay, and so basically the current just goes through here. This is virtual ground, anti-symmetric point. Basically, current just flow from left branch to the right branch. However, on top is a current mirror. Even in small signal mode, the current mirror forces them to have the same I. So the small signal current coming down here is still I. So if you do a KCL at this node, for your AC current, you'll find that, 2I must flow out from this single-ended output. So you have I coming up from the node and I going down from the node. So the only place current can flow out is to the output node. So that's the 2I AC current. So you gain twice of the gain. So the gain of this amplifier is exactly the same as you take the difference of the original differential amplifier. Here you have basically the same gain, okay? If you look at just this transistor, you are applying only half of the voltage here. You get twice twice of the current out, and you gain basically the same amplifier, same amplification factor. So this half circuit give you twice output circuit from just one side. So instead of taking the difference where you get your doubling from taking the difference, the current mirror is doing the internal doubling and converting to single-ended output. So you have the same, you end up having a same gain, same differential gain as the and same differential gain. But single-ended output. Okay. So a nice trick, simple trick, but works very well. So at the very last stage of the differential amplifier, if you cascaded several of them, last stage you usually see this trick. Okay, any questions? All right. So let's see kind of the more complex circuit. Well, before we look at this most complex circuit, let's kind of go step by step. Okay. So now, two-stage amplifier with differential input. So here there are 8 transistors, very complex circuit. Yes, questions?
Sorry, really quick at the end. So at the output of the last stage of the differential amplifier,
Yeah.
you would get the original difference of the two signals, but relative to the ground instead of just.
Yes.
Okay.
Yes.
So it'd be like the original signal minus the.
Right. So you get basically the difference coming out from just one side. Okay, all right. So let's get back here. This is A transistor circuits. And again, let's usually identify the key transistors or key blocks. Let's look at the key blocks. And what block do you see here? So where are the inputs? So here is minus and plus. These are like minus and plus lead of your OP amplifier. So obviously Q1 and Q2 are important part that forms your differential pair. Okay, and differential pair needs a current source. So Q5 is basically a current source, right? And it's mirrored from Q8. So it's somehow related to this reference current source. So this stage is a differential pair. Differential amplifier stage, okay? And if you look down here, it has current mirror node, current mirror load. So Q3 and Q4 give you current mirror load. So that means we converted output to single-ended. So here is your output, right? So it goes to now just a single-ended amplifier. So here is our second stage amplifier. What amplifier is this? Q6 and Q7? Common source, yes. So you go back to common source, just a simple single-ended common source amplifier. And you feed the output from the input. There is a capacitance here. This is for stability compensation. If you are interested in knowing what these capacitance do, you go take EE140. You will talk about this in great detail. So here we just say it's basically giving stability to the amplifier. When the gain of amplifier is very high, sometimes the amplifier began to oscillate by itself. So whether you have signal or not, it's already oscillating back and forth. So that's undesirable. Okay, so ignore CC. What you noted here is there's no coupling capacitance. Around your lab 5, we talk about between stages there are coupling capacitor. Between the bias network and the transistor, there's a coupling capacitor. So here is entirely DC coupled. Okay, all the bias are generated to give you the right bias voltage, thanks to largely the current mirrors. So the current mirror give you all the biases that you need. Okay, so you have all the biases here. And Q7, the gate goes to the same gate as the current mirror. Everything here are all nicely biased, okay? The only point that you might be kind of asked question is Q6. How is Q6 biased? Q6, so now we already bias Q7. Q7 already determined the current because VGS, so we already know the VGS of Q7. So the current is fixed here. We do not want to set a separate reference for Q6. Then, two transistors will start fighting each other if you set them at a different VGS. So obviously you don't want to connect a separate voltage bias here. It's connected to the desired previous stage, the output of the previous stage. Remember, in this transistor, the DC voltage between the drain is actually free to move quite a bit. So the drain voltage here can actually move up and down quite a bit. So it will self-select the voltage point so that the current flowing through I6 will be equal to I7 because there's no other path. So we kind of naturally bias Q6 in the correct bias through this kind of clever way of doing the DC wiring. Okay, so this is reading the circuit, current mirrors on top, differential pair with current mirror load, common source amplifier. Okay, so now the function looks pretty straightforward. You don't need to do small signal model for every transistor. Okay. You can estimate the gain quite easily here, right? So we do it block by block. The gain of the first block here, right? So this is a differential pair, and it is gain of GM1. So it's a GM1 times the output resistance. Output resistance, you look up, you see RO2. You look down here, you see RO4, okay? So the gain is simply the transconductance of both Q1 and Q2, they are the same, and times the output resistance of this particular stage, which is RO2 in parallel with RO4. So this is kind of a high-level view of reading the circuits. You don't really need to do a small signal circuit to get that. It fits into one of the standard models. Okay, and you can estimate the gain of the second stage separately. Second stage Q6 is the main amplifier. So it's you use the common source gain. So it's GM times output resistance. Output resistance here is parallel combination of what you look down, RO6, and what you look up is RO7. Okay, if you have a load, it's further in parallel with the load. Okay, and the total gain is the product of the two. So you kind of go block by block. That's why we study the basic building blocks that help us estimate the final performance in a much more scalable way. Yeah?
Can you please explain again for the gain for stage 1?
Gain for stage 1.
Yeah, why do we only focus on GM1 instead?
So it's kind of compressing a lot of things we have learned in the past couple of lectures. So this basically says, okay, if we have a simple active load, okay, and if we have a differential pair here, okay, and so if we do this, and this is active load, right? And if we do the differential VID plus over 2 minus VID over 2, we convert this first to half circuit. So half circuit is basically, right, common source mode. And here will be VID applied here, right? So the gain, half of